In today's lecture, we are going to discuss about nuclear magnetic resonance NMR. Basically, we will discuss about the basic principle of NMR and interpretation of NMR spectrum. Okay. First of all, let's discuss about basic principles of NMR. The nuclei having odd protons or odd neutrons have nuclear spin, and with this nuclear spin there is associated magnetic moment. Such an atom acts like a magnet. So we can use NMR spectroscopy for those nuclei that have spin, because the nuclei that have spin acts like a magnet. We'll use that property, that is magnetic property of the nuclei. That's why nuclear magnetic resonances, we have to put the nuclei into same orientation. That's the resonance. Okay. Next important thing is, in NMR spectroscopy, external magnetic field is applied to the nuclei to put them into alpha state, and also we use certain type of electromagnetic radiation which we can call radio frequency energy to put atoms, that is nuclei, into resonance, and we will measure that energy. That is, we will measure the radio frequency energy required to bring atoms, nuclei, into the resonance. Okay, clear? Then next thing is amount of energy needed, that is radio frequency energy needed to bring atoms into resonance in same direction, same orientation, depends on the electronic environment they have. That means some nuclei may have shielded by some electrons, and some others are not shielded, that we can say de-shielded or dimagnetic shielded. Okay. Next thing is, in NMR spectrum, finally we get a spectrum, a plot, in which there are peaks, which represents the energy required to bring the nuclei into the resonances. Okay, these are the basic principles we utilize, exploit in NMR. Okay, now let's see a nuclei. Suppose you have a hydrogen nuclei. It has one proton, that is odd number of protons. So in NMR we need a nuclei that have odd number of protons or odd number of neutrons, or both. It will be more clear in next slide. See, in this slide, let us take a hydrogen. It has one proton and zero neutron. That's why number of proton is odd. So it has spin. So we can use this for NMR. Okay. In case of deuteron, see this atom. This is deuteron. This has one proton and one neutron. So number of proton is also odd and neutron is also odd. This shows that this atom also shows spin. Okay. Let's see in case of helium. What's the helium atom? In helium atom, number of protons is 2 and the number of electron is also 2. This nuclei do not have odd number of protons or neutrons. So no spin. We can't use helium for NMR. Okay. Similarly, carbon 12. It has 6 protons and 6 neutrons. So no odd protons or neutrons. So no spin and no nuclear magnet. That's why we can't use. Okay. Let's say now this one, black one, is a nuclear magnet, and blue one is external magnetic field we had applied. Okay, when we apply magnetic field, the nuclear magnet will orient in the direction of applied magnetic field. Okay, this state of nuclear magnet is said to be alpha spin state. Okay, this state has lower energy because it's oriented in the direction of magnetic field. Okay, clear? Now, somehow, if nuclei get energy, suppose electromagnetic energy, it will orient opposite to the direction of magnetic field, external applied magnetic field. This state is said to be beta spin state, and in this case there is higher energy, so it is said to be higher energy state. Only few nuclei could be in this state. Okay, now let's see first what is shielding and deshielding. Suppose that you have a nuclear magnet. This arrow represents a magnetic direction of the nuclei. This acts as a magnet. So this is represented by a vector. Okay. In this nuclei, there are no electrons shielding. That's why this is deshielding or diamagnetic shielding. In this one, at right hand side, there is shielding. Sorry, this one is diamagnetic shielding. So around this nuclei, there are electrons surrounding. So this is shielding. Okay. So this is concept of shielding and deshielding. Let's move to the next slide. In this, see on the left hand side, if you apply external electromagnetic radiation to this sample, then what will happen? It will flip to the opposite direction of applied magnetic field. Energy required E1 will be more because it has to flip, nuclei has to flip by 180 degree. But in this case, because of shielding, diamagnetic shielding, the nuclei is already oriented like this. So energy required to flip into resonance state, that is alpha state, will be less. It will be more clear on next slide. See right here, we apply electromagnetic radiation, basically radio frequency energy, for both, from here also and from here. Okay, for this one which is not shielded, deshielded, requires more energy, so E1 is high energy, but right here E2 is less because this arrow is small, so energy required to flip the shielded nuclei is less. Okay, this is the equation from where we can calculate the energy. Delta E is equal to S nu, where nu equal to gamma by 2 pi B naught. NMR operating frequency, it is said to be NMR operating frequency, and gamma is gyromagnetic ratio. Beta naught is the external magnetic field we have applied. Okay, now up to now we discussed about the principles behind the NMR. Now, how to interpret the NMR spectrum? Let's take an example. Suppose that we have a molecule like ClCS2CS3. Okay. Right here, you can see this one is a hydrogen atom. This is a nuclei having spin. So, close to this nuclei, there is chlorine. Chlorine is an atom that is electronegative in character. That means it can attract electrons towards it. That's why electrons are attracted by chlorine, and this hydrogen atom becomes a dissociated. So higher energy is required for this one to put into resonance. But in case of this hydrogen, because electronegativity is a local effect, what does that mean? That means it will not affect the atom that is farther away. So this atom right here, say B, is far away from this chlorine. That's why this is shielded by electron. Okay, so lower energy is required. So in NMR spectrum, you can see this is the energy line, and you can see right here this signal is for B. Energy required is less. See right here, this is increasing energy, so this is less, and this is high. That's why we can say what type of atom is present around that atom. From this graph we can know that. Okay, let's make more clear how this technique, that is NMR spectroscopy, is different from FTIR or mass spectroscopy. Okay, in case of mass spectroscopy or FTIR, there may not be difference between the same type of the molecule. I mean, suppose this molecule and this molecule have same number of hydrogen, same number of carbon, and same number of chlorine. So all other techniques may not differentiate, but NMR can differentiate this molecule with this one. How? Let's see. This one is supposed say A, this one is supposed say B hydrogen, this one is supposed say C hydrogen. Let's look at first A. This one is dissociated because chlorine is close by. Okay, if it's a dissociated, amount of energy required to put this hydrogen nuclei into resonance is more. That's why this peak will come the farther away from the origin. Okay, then this one is also close by this one, but not like A. That's why another peak for C comes between right here. But in case of this one is far away from the chlorine, so this is shielded. So less energy is required to put this atom into resonance. Okay, but right here, if structure is like this one, what will happen then? In this case, this hydrogen and this hydrogen is like same distance. That's why the energy required for this one and this one is same, B, and this one is closer by, so more energy is required because this is dissociated. Here is a chlorine which is electronegative, and it will take out all the electrons. Effects of all the electrons goes to right here, and this is dissociated, not shielded. So energy required to bring the hydrogen nuclei will be more. So right here, the peak of NMR spectrogram is hard. Okay, thank you.